record for today. So we're on section 2.3 still, and we're still looking at free-falling objects.
Mr. Howell, can you give us the negative 9.8 with
You should memorize that, okay? I can give it to you on the test because it is given on like AP exams. It's actually given, but you should know that by now. Acceleration due to gravity is negative 9.81 meters per second squared. Something you really should memorize. All right, so for this problem, there's going to be parts A, B, C, and D. So we have a toy rocket launched. Again, this is a very good problem for your test. The toy rocket is launched with a velocity, not N, but A, correct that? Is launched with a velocity of 25 meters per second, and I'm going to put straight upward. Okay, meaning it's upward and it's perpendicular or normal to the surface. There's no X, yes, very good. I don't know if straight upward is the right way to say that.
Straight up.
Does it sound straight up? Thank you.
Straight up.
My English is way off. Sorry, guys. Straight up. Okay. So, again, whenever this is said, think about a rocket or a toy object. It's not launched at an angle this way, anyway. It's launched literally straight up. Okay? That's straight up. All right. After how much, part A, after how much time, or after how long, we could just say, after how long will the rocket reach its max height? And we're going to do these in parts. We'll do part A first, then I'll tell you part B, C, D. After how long will the rocket reach max height? Its max height. Okay. After how long will the rocket reach its max height? From yesterday's class, what did we say about max height? We made a characteristic. We made some sort of a statement about the rocket when it hits the max height. Nasha. Very good. That's exactly right. Can everybody hear that? One more time, Nasha. Nice and loud. Well done. Why? Who can explain why now? She clearly knows. Who else knows why? Tyson.
Because once it gets to the top, you're going up and you have a positive acceleration, and then once you stop, since you're going down, you have to have before you can go negative, you have to have zero.
Yeah. So you have positive velocity. Be careful. Positive velocity the whole way up. It's got to stop so that it can turn around, right? And have negative velocity then. So when it reaches that peak, remember the word peak used yesterday? When it hits the peak, it's got to stop. And then what happens is it falls back down. So there's an instant in time where the rocket will stop, and that's at max height. So, for this kind of a problem, here's what I want you to do. Please draw a diagram. Here's your diagram. Rocket being launched. Stop the comments. Initial velocity is 25. I know that the initial velocity is 25 because it says it was fired with 25. Stop. You're really pushing it down. Pushing it. Now, your initial is 25, at the top it's 0. Now, I label the top as VF because I'm thinking of this as a segment. Remember, a segment. All I care about right now is where it's fired from to the top. I don't care how it returns. The next part of the problem, we're going to talk about how it returns and everything. But all I care about right now is beginning to end, being from the ground to max height, from point A to point B. Next. What else do I know about this problem that I'm going to need?
Boy, don't you need to know? Do you need to know the distance for this or no?
We're going to learn the distance soon, but right now it just says how long will it take. So we're looking for time. Good. What's the acceleration? Negative 9.81. Come on, guys. Doesn't matter. Which way does gravity always act? Again. in yesterday's class, we talked about gravity being negative 9.81 meters per second squared as acceleration. This is really what's called G.
So gravity is always acceleration?
Whenever you're looking at an object moving vertically, the acceleration is always going to be this quantity, unless there's some outside force. So for example, if you have a rocket booster launching a rocket that has its own acceleration of 2, then the overall acceleration will be negative 7.81. Again,
Why does this not have any acceleration? I mean, doesn't it have acceleration?
it does because, think about it, if I toss this up, what's causing it to come back down?
Gravity.
It's the acceleration due to gravity which is pulling it down.
Isn't
But
that
your
starting with
throw is
I know, this is tough to think about. Your initial velocity is launched at 25, right? But once it's launched at 25, there's no more acceleration because it's slowing down the whole way up.
That makes sense.
Okay? The acceleration is always going to be this negative quantity. Sure, Jeff, at the very instant when it's launched, there's some other acceleration which causes it to be launched. But we're looking at from the launch speed of 25 to the ending speed of 0. Okay? Now remember, if this was a rocket, it might have a rocket booster which has its own acceleration upward. So if the acceleration from the rocket is 5, you have to subtract the 5 from the negative 9.81 to see the difference. I'm saying, I'm saying, yeah, initially yes, but I'm saying if there was some acceleration during the flight, if there was some, like, ever see a rocket booster shoot like fire out the end of it? So thruster, that's what it is. There's some force of thrust acting down, which causes acceleration acting up. So throughout the flight I'm talking about, yes, initially you need something greater than 9.81 to overcome that feeling. Just like, think about it, if you guys jump off the ground, if I just go like this, and I try and jump, am I going anywhere? My acceleration is not greater than 9.81. That's why I'm not going anywhere. But if you actually jump off the ground, your acceleration is exceeding that. Until what happens? Once you're in the air, then the acceleration is pulling you back down. So we're assuming you're already kind of in the air. Okay? What formula should I use for this? What formula? What am I solving for again?
Oh, T.
Time.
Okay, so, sorry, I was actually going to ask something else.
Yes, yes, yes.
I was completely off topic. No, but it's like interesting. It's
What are you doing this for, dude?
We'll come back to it. What formula is this one? What formula are you guys? Paul.
Delta V over A is, yeah, T equals delta V over A.
X over.
Okay, that works, but maybe for now, just give me one of the kinematics. Give me one of the 3 kinematics. That does work though, Paul, absolutely. Which of the 3 kinematics would I use if I had these variables here? What you said was right, Paul, so I'm not saying you're incorrect there, but just to stick with my kinematics for now.
VF VI DAT.
VF equals?
VI plus acceleration times time.
Good. And Paul, when we solve this for time, we're going to get the equation you had. I just want to show that. Okay? All right, let's do this. So, I want to get time by itself. Several of you asked us, several of you asked common sense questions about whether you can plug in numbers first. You can always do that. So at this point in time, if you want to plug in all your numbers, that's fine. It doesn't matter. But I prefer to solve for the variable. So I'm going to subtract VI, and then I'm going to divide by A. Okay? Again, I'm going to subtract the VI, then I'm going to solve for T by dividing by A. But again, you can plug in numbers. Nice.
No, I was just going to say, like, you could just like take out VF and
Yeah. Oh yeah, VF you could drop off too. You're right. VF is 0, so you can go like this for this one also. Absolutely. Absolutely. All right, so let's plug in now that we know. We know we have 0 minus VI was 25 meters per second. The numerator. The denominator is negative 9.81 meters per second squared. That equals T. Notice I have a negative over negative, which yields a? I have to have a positive because I'm solving for time. If you get a negative time, you made a mistake. If you get a negative under a radical, you made a mistake. You can't have imaginary answers. Okay? So negative 25 over negative 9.81. Molly?
It's 2.5.
Good job, Molly. All right. Next. Again, the time it takes the rocket to get to max height is 2.55 seconds. Now, what I'd like to do following is this. What is the actual max height of the rocket? What is the max height? So I'm asking now for what? What is it? X or length. Good. X or length. So for this next one, what formula might I use for the next one? Jeff?
Couldn't you do G equals first, G equals X over V?
That's only for when there's no acceleration. Don't forget, that's chapter 1, when there's no acceleration. Or section 2.1. We're now looking at this acceleration. Yeah, use one of your kinematics. Guys, you're traditionally going to use the kinematics. Whenever there's any acceleration, use one of the 3 kinematics. Okay?
Squared minus VI equals X, or it's over 2A.
Okay, very good. So solving this for x, what Jeff is doing is, he's solving this for x and saying, vf squared minus vi squared all over 2a is equal to x. Yeah, we can use this one, because we know vf, we know vi, we know acceleration. Again, we were given vf is 0, drops off. Again, vf is 0, that one drops off. The initial velocity is 25, the acceleration is negative 9.81, so we can use this equation. What's the other equation we could have also used, though, really?
X equals velocity, initial velocity, times time plus half a.
Good job, Lourdes. You can use this one as well. We got the time from the first part, which enables us to use this equation. Had we not solved for the time in the first part A, we would have had to use this equation to get the max height. Okay, because again, we were given VF, given VI, given A, solve for X. But since we know the time from the first part, it might be easier to use this equation down here, because it's already solved for X. And you may not want to memorize this whole thing. You can, but to memorize is annoying sometimes. So you could use either equation. It does not matter. It does not matter. So I'm going to say X equals VIT, which is 25 meters per second, times 2.55 seconds, plus 1/2, negative 9.81 meters per second squared, times 2.55 seconds squared. That's really messy at the bottom there, sorry. The board doesn't work at the bottom right.
Yeah, it looks like a ball.
Okay? Again, that's a 2.55 there, and we got to square it. That's 2, there's a decimal. So again, you can use this formula, or if you wanted to, you could use the other formula that we had earlier. You're going to get the same answer. There's no difference here. You should get 31.85. Why do I know it's positive? Because I'm moving upward. Remember, the max height was upward. Right? Jack.
What's the 2 in the bottom? A T.
1/2. Sorry.
Oh, okay, sorry.
That's just me not reading French. Yes, and again, we're looking at displacement, or the distance from the ground to max height, which must be in meters. Okay. Now, these next 2 parts are going to blow your mind. Mind will be blown. Too late. They're like that. Part C. What will the velocity be at the instant it hits the ground? So now we're looking at the problem where it went all the way up to the top. Stop it. Came all the way back down. Enough, guys. You're really testing the waters here. Please don't do that. So the rocket launched up. It reached the top at its max height. It turned around and came back down. I want to know, what is the velocity down here at the bottom when it hits the ground again? So,
Isn't it 0 or between like before it's
the second, the input velocity, I guess, right before it hits the ground, not after. What kind of a problem can I think of this as now?
How much does it accelerate from one point to
On the way back,
Yeah, what would be like the velocity, an acceleration of 9.81, 31.5.
okay. What would the initial velocity be for this problem is? Why?
Because you're reaching the max.
Yeah, so everybody, take a look up. You're starting from here now. with a velocity of 0. This is like a second part of the problem. Think of only the second half of it. The first half it went up, right? The second half is coming back down. So now it stopped at the top. So now it's got a velocity of 0. We want to find the final velocity at the bottom. We know the displacement is going to be 31.85, but with a negative sign now. Because now I'm going down. This is now like a free fall. The object has launched up, it got its max height, and now it's being dropped to the ground. Okay? Again, it's like the object went to the top, it stopped, and now it's being dropped to the ground. So we think of this problem as a VI of 0, a displacement equaling x of negative 31.85 meters, and we're trying to find the final velocity. The acceleration is still the same. What is it? Good, negative 9.81 meters per second squared. So this problem is like a symmetric problem to the original. You see the symmetry involved here? Okay, now we have an initial velocity of 0, and we're trying to find the final velocity instead. Jack and Max.
Why is it negative on negative 31.?
Because now you're starting up here, and you're ending down here, so you're traveling negative displacement. Max.
If something is like pushing, like if like a fan is pushing a piece of paper around, would the acceleration still be negative?
Depends on what you're looking at. Like
if it goes up and then the fan turns off and it goes back down.
the fan launches the paper up,
Yeah.
and the fan turns off, and then it starts coming down.
Would the acceleration be negative the whole time, or just?
On the way up, the acceleration from the fan would overcome gravity. Okay? It would launch it upward, but it would still be slowing it down on the way up gravity until it reaches the top. And then you're saying you just shut the fan off suddenly,
Yeah.
and then the acceleration will be negative on the way down.
Yeah.
Okay? All right. So with this problem, what might I want to do?
Wouldn't it be the same as the initial velocity?
Well, that's what we're trying to figure out. What is it going to be? That's a good hypothesis. I like the hypothesis.
Because it travels the same distance, the same acceleration.
Throughout the whole path? It does. It does. The initial velocity is 0, and we're trying to find a final. But Sasha is saying this final will be the same as the initial that was launched. So you're saying we'll get 25, right?
It has the same force affecting the bottom as well.
Yeah. The acceleration is affecting it on the way up the same way it's affecting it on the way down. So theoretically, we should get the same answer. And let's take a look and see what happens, okay? So I know VF, I'm looking for VI, A, and X. So right away, I'm going to go to the formula. Again, how do I know this? I know VI, it's 0. Acceleration is negative 9.81. X is negative 31.85. We can solve for VF. Cross off your VI, because it's 0, because we're now dropping the object, really. We know VF is equal to radical 2AX with a plus or minus in front.
Oh, it's the same.
We say VF equals plus or minus 2 times, under the radical, sorry, negative 9.81 times negative 31.85. Negative, negative becomes a?
Positive.
Positive. We're going to have VF equals plus or minus 25. Does that ring a bell, like Stash just said?
Yeah, it does.
What was our initial velocity, guys?
25.
It was 25. Okay? If you multiply this and take the square root, you'll get 25. Trust me there. Now, plus or minus, which one? Minus. Minus, because it's coming downward. Okay?
It's still going.
No, it's going down.
So think about this for a second, people. It's launched, it gets to its max height, it then turns around and comes back down. That's why in this problem we have a negative in the symmetric or the reflection of the original. Okay? Now, another way to solve this problem, just so you know, we'll get to part D in a second. You could have said this. You could have said the following. It's launched up, it comes back down. You could have thought of the whole problem from the beginning of VI is 0, VI is 25. Okay? You could have said, what is VF? And you could have said, what's the displacement? If an object is launched up and comes back down, what's the displacement, everybody?
0.
0. So you could have solved this problem by saying the displacement is 0, the initial velocity is 25, find the final velocity, and you'll get negative 25. It's the same problem. Again, instead of solving this problem from the second half, from here down, you could have solved the problem the entire way, okay? From the bottom to the top and back down. If the displacement were considered to be 0.
What was the initial velocity?
25.
We didn't know that.
We did, that was given in the problem. The problem was given as the initial velocity is 25. If we think of the displacement as 0, and you solve using Vf squared equals Vi squared plus 2Ax, you'll get Vf equals negative 25. It's the same
When
thing.
did we know that?
Say again?
Just guess that?
Now that you know that, you could always say that, absolutely. But prior to this problem, did you know? Not necessarily. Stosh made the hypothesis that we proved to be true. Okay?
That's only if you have the same distance.
That's only if you have an object being launched from the ground and coming back to that location. If an object is launched, right, and it like somehow in the middle on the way down lands on like a ledge, it's not going to be symmetric anymore. Are we clear on that? It's launched up, and then suddenly while it's coming back down, a ledge is extruded from a building and it lands on that ledge. It's not going to be 25 anymore because it didn't come back to its origin. Whenever it comes back to the origin, symmetry does exist.
Displacement's still 25. Wait, sorry, no, it's still the same displacement. Wait, it's a different distance or no?
Yeah, because here, if you launch it up and then a ledge shoots out and comes back down, the overall displacement is from here to here. It's not 0. Like this problem, the displacement was 0 for the whole thing. Okay? Part D. Part D. And try this tonight because we're going to run out of time. 2 parts to it. How long will it take the rocket to return to the ground from the max height? How long will it take the rocket to return to the ground from max height? Second part, what does this say about the overall time of the trip from start to finish? So how long will it take to get from max height back to the ground? Second part, what does this say about the time from the bottom all the way back to the actual ground, the entire time of the trip? And you'll notice a correlation here. Okay, you'll pick up on it. Okay, so tonight you're doing that. What else would you like you to do tonight? Please, please, please. Go online and look at my notes. They're online. Look at the last example at the bottom of the notes. Okay, and then you'll see the homework is there. Start the homework tonight. Give it your best shot. You'll be fine with it. So again, tonight, you're going to do the homework under acceleration. I'll put it on Moodle under homework, but there's also a notes document, section 2.3. Look at the last example also and read through it, please.
Sounds good to me.
Don't forget tomorrow, what's due?
Homework.
Work on the homework and your problem sets are due tomorrow. The homework is to finish this problem. Read the last problem. I put the other homework at the bottom, but you might have left to do the problem set.
With the stuff you just said, homework.
I don't know. Yes.
Well, Mr. Howell.
Have a good one. Can't use that because this is assuming there's no acceleration. This is saying acceleration equals 0. So if you want to derive that formula, you want to combine. You just move my stuff from the You're welcome. Thank you for that. Tuck that shirt in. Thank you, Paul.
Hey, you got all this new equipment?
Stash, you don't have class.